Yes, welcome to a presentation of synthetic fuels. My name is Holger Watte and I work at Flensburg University of Applied Sciences in the field of ship operation and energy science. I also work for various associations in the professional field. A special focus of activity is in the area of quality management and energy management. This presentation will deliver basic knowledge of synthetic fuels. It is structured as follows: discussion basis, synthetic options, reaction equations, mass and energy balances, reaction kinetics, and conclusions. First, a reminder of what conventional fuels are and what they are made of. They consist of long-chain hydrocarbons with different change lengths. Next, what does synthetic fuel mean? Definitions of terms and options for actions. In nature, the term is based on photosynthetics. Nature rearranges molecules and substances and thus creates new substances with special properties and energy content. Through technical measures, for example in the case of biomass, synthetic fuels can be produced in various ways. In the case of synthetic fuels, the following are presented: power to gas, reaction equations, reaction kinetics, energy and mass balances. Electricity-based synthetic fuels are based on the utilization of wind energy with help of electrolysis. If you look at the details of the electrolysis, 9 kilograms of treated water are required per kilogram hydrogen and 55 kilowatt-hours per kilogram hydrogen. The water requirement can be met with rain, sea and sewage water by reverse osmosis. With reverse osmosis, only the poor water penetrates the semi-permeable wall. It is known from the ship operation that approximately 20% of the water can be used as permeate. Taking into account the previous calculation, approximately 45 kg of water per kilogram of hydrogen are required. The energy consumption is relatively low. An example calculation for an onshore wind power plant shows that due to the wind distribution, around 25% of the nominal power is available on an annual average. In the case of 1 megawatt wind power plant, around 4 or 5 kilograms per hour can be generated with the above mentioned efficiency level. The economic reason, the investment, operating and previous costs should have also taken into account. The gas network operator sets upper limits for the feed in the hydrogen because of hydrogen exbrittlement, firing properties, flame pattern, heating capacity, named as Wobbe index, reliable, reproducible ignition properties in the milliseconds area for engine combustion. One possible solution to this problem is the methanization of hydrogen. Let us consider the details, such as the reaction equation, as well as energy and mass balance. The mass balance shows that per kilogram of methane, 2.7 kilograms of carbon dioxide and 0.5 kilograms of hydrogen are required. The gas purity is determined by the position of the equilibrium. In chemical processes, an equilibrium is established that is never on one side or the other. Pressure and temperature also determine this gas purity. The energy requirements can be determined according to the Hess theory. With the standard enthalpy of formation results, that at least and theoretically almost 3 kilowatt-hours of energy per kilogram of methane are required. The available caloric value or energy content of methane is 55 megajoules per kilogram or 15.3 kilowatt per kilogram. The generation effort is therefore approximately 18% of the later usable energy content. Taking into account the energy requirements for hydrogen generation, approximately 30 kilowatt hours per kilogram methane are necessary. The theoretical relationship must be clear in the further considerations. The comparison with practical results shows that the effort is much greater than the benefit, or the benefit is less than the effort. The usefulness must be checked. The consideration of the degrees of efficiency in the utilization chain also gives poor results. 5 times the amount of energy should have been made available in electricity. The other options regarding e-fuels should therefore also be examined as follows. Power to fuel means there are various ways of producing liquid fuels. Carbon monoxide forms the basis for this. For this purpose, the carbon dioxide is splitted up with the help of hydrogen. The equilibrium position depends on pressure and temperature. The decomposition of carbon monoxide into carbon and carbon dioxide as boundary reaction is exothermic. Energy is released. The figure shows the position of the equilibrium as a function of temperature. Using the example of medium-sized diesel fuels, the energy mass requirements can be shown. The pentadeck with 15 carbon atoms, 2.7 kilowatts per kilogram of diesel are required. The energy expenditure depends largely on the length of the carbon change. This corresponds to approximately 23% of the caloric value of the commercial available diesel fuels. Including the hydrogen requirements per kilogram of synthetic diesel, there is an additional of 16.5 kilowatt-hours per kilogram diesel. Taking into account the CO2 coal monoxide shift and the enthalpy of formation, a total of around 20 kilowatt-hours per kilogram diesel is necessary. 1.7 times of the calorific value of conventional fuels, more effort than benefits. The reason of this is that around 1.2 or 1.4 of water are produced per kilogram of fuels, and around half of the hydrogen used has to be used to produce it. What about methanol? Methanol reaction with Fischer-Tropsch synthesis delivers in principle similar mechanism as above. In the energy balance, methanol is slightly ahead of methane. As a liquid fuel, however, it has a significantly higher energy density and thus shows logistic advantages, especially for ships. What about ammonia? The reaction equation and the mass balance provides the requirements of nitrogen, the main component of air, and hydrogen. And the energy balance delivers a very large hydrogen requirement here too. Hydrogen remains the special central element in the production of synthetic fuel as at all. Let's summarize. It could be shown that the required processes are extremely complex and not trivial. Hydrogen production is a key technology in all processes for synthetic fuels because it is a central component of production chain. Currently, for reason of cost and volume, the steam reforming of hydrogen carbons based on mineral oil dominates worldwide hydrogen production. The wind distribution, the characteristics of the wind power plant, and the efficiency limitation of the electrolysis show poor results because they do not come to the necessary full load hours alone, and more characterized by non-availability. Significant increases in efficiency against the physical limits are not be expected. They are in the single-digit percentage range. The wind distribution offshore shows greater potential. Larger full load hours can be expected offshore. The energy and mass balance of synthetic fuels show more effort than benefit. Thanks for your attention.